I want to give you insight in terms of how we actually determined the line of best fit to actually be the one that's considered to be the best fitting one. And so the way that we go about the linear regression is using a method that's called least squares regression. So the first thing that we need to understand is that of residuals. So if you have a set of data, so you have all of these ordered pairs right here, and then you fit a line to those ordered pairs like you see, then the vertical distances that you see with these red segments right here, those are the residuals. So the residuals tell you how far away vertically we've landed. And then if you just use those red distances and you make squares out of them, then you get all these squares. And it turns out that the line that would have the least amount of area by all of those squares is considered to be the one that's the line of best fit. So you can kind of see a completed example of squares, and I'll do a manipulation in just a little bit right here, which will help you understand more about what's going on right there. So when we talk about square residuals are just making actual squares out of the residuals themselves. I did take the Arctic sea ice data, and these green dots right here, they seem to follow the same pattern, which is of course true, but they're actually showing the residuals, and it's easier to understand here. So for example, right here, that negative 0.649, that's one of the residuals, and what that's telling you is it's telling you that for that very first point right here, it actually fell that much vertically away from where the line actually is at, so it was like negative 0.6 whatever away. So a residual will always be negative if it's below the line, and positive if the dot is above the line, and then of course 0 if it's on the line. Here I want to show you this process of least squares regression and help you really conceptualize how it actually works. So I'm just going to pick a random data set here. Let's do height versus shoe size there. Okay, that'll work. So right now our line of best fit is graphed as just y equals 0, x plus 0. So just y equals 0, and there's actually a little blue color right there. So if I click this right here, it's going to show us the residuals, and so all the residuals are going to be positive right now because all of these points are above the line. And then if I make the square residuals, it turns and makes squares. They're obviously very large because the line is far away. So I can manipulate the A value and the B value here using these scrollers. So if I change the A value and I make it higher, of course it's going to make it have a more positive, steeper slope. And then the B is going to change the y-intercept, make it go down, make it go up. We want to make it go up. And so right there, if I just stop it where it's at right now, we've got a line that's closer to fitting the data. Now clearly this is not the line of best fit. And so we can recognize that the areas of these squares are a lot smaller than they were before, and ultimately the goal is to make the total sum of all the areas of these squares the smallest. This bar right down here is kind of tracking my progress in terms of how I'm doing, so the smaller I make that bar, the better I'm doing. So to get this a little bit better, I'm gonna have to make this slope actually be a little bit less steep. That would probably be a little bit better, and then increase the y-intercept quite a bit more. And so once we get somewhere in there, we're doing pretty good right there in terms of finding a line of best fit, because some of the squares areas are pretty small. So then that would be pretty close to what the regression equation would be right there, 2.31x plus 44.7.